I want to work through this problem 7.10 in Kleppner and Kolenkow, the cylinder in a groove problem, which is marked with a little star because it's somehow harder than the others, but we'll see. So this problem has a cylinder spinning in a V-shaped groove. It has mass big M and radius big R, and there's a coefficient of friction, and due to that friction, the cylinder would tend to slow down in its angular rotation. But instead we're going to have a guy standing there who torques this cylinder, who keeps it spinning, and he applies a torque so that this cylinder keeps moving at constant angular speed omega. So we want to find what is the torque that must be applied in order to keep it moving at that constant angular speed. So let's move over here and draw the situation. So I have drawn the cylinder and the 2 points of contact. And we're first interested in what are the forces acting on the cylinder. So, of course, since it has a mass big M, this guy has a force big mg acting downward due to the weight. And now in these two places where it makes contact with the groove, there's also going to be a normal force from each. So, I haven't drawn this quite symmetrically, but let's let the normal forces be N sub L and N sub R for the two parts, the two points of contact. And now let me draw in the rotation. So the cylinder's moving with angular velocity omega. And now the friction is going to act to oppose that motion. So at this point of contact, the cylinder is going counterclockwise, so friction is going to act like this in the opposite direction. And I'll label that with an F sub L. And at this point of contact, likewise, we're spinning counterclockwise, so friction acts like this. And I'll call that F sub R. And I haven't drawn it here, but we were told in the problem that this angle here is 45 degrees. And you can convince yourself by doing the geometry here that that means that each of these forces is going to make a 45-degree angle with the horizontal, which will be helpful. Good. So now let's see what we can do with these forces. So we know that the cylinder is moving with a constant angular velocity, but it's not translating in the x or y direction. So we have equilibrium, linear equilibrium in this problem. So we can use that to write down two equations of motion. So let's see, x equilibrium in the x direction. So what are the forces in the x direction? Well, we have the friction force on the left and on the right both act towards negative x, so I'll write minus F sub L, and now the component of F sub L acting in the x direction is just going to be FL cosine of 45 degrees, but that's 1 over square root of 2, so I'll put that in right away. So minus F sub L over square root of 2, same thing with the right frictional force, minus F sub R over square root of 2. And now the two normal forces, N sub L acts towards increasing x, and N sub R acts towards decreasing x. So these guys sum to 0. And what about the y direction? Well, y equilibrium. Well, so we have mg acting down, so minus mg. And then we have a similar decomposition where each of these guys gets this square root of 2 contribution, but now we see that they're all acting up except the friction force on the right side. So this will look something like plus F sub L over square root of 2 plus N sub L over square root of 2 plus N sub R over square root of 2 minus F sub R over square root of 2. That whole thing gives 0. Very good. So where do we go from here? Well, we need to eliminate these F sub L and F sub R, because otherwise we can't solve. So we're going to use the condition given that the coefficient of friction is mu, which gives us a relationship between the frictional force and the normal force. And since the cylinder is slipping, we know that friction's at a maximum, so we can apply that. So let's just draw that in. So we'll call that F sub L is mu times the normal force, and F sub r is mu times its corresponding normal force. So we get in the top equation, I'll just multiply through by square root of 2 to get rid of all of those. So what do we have here? This will be a mu times n sub l, so that means n sub l times 1 from this minus mu, 1 minus mu. And then here we have minus n sub r times 1. This will also be a mu, so it should be 1 plus mu, I think, equals 0. That gives us one equation. And then in this equation, we can move the mg over to the other side and multiply again through by square root of 2. So it'll be on this side equals square root of 2 mg. And on this side, let's see, so this will be a mu times n sub l, so we'll get an n sub l times 1 plus mu. And then over here, this will be plus n sub r times, we have 1 minus mu, I think, on that guy, so 1 minus mu. So these are the two equations that we get using the definitions and these friction constraints. So now we want to go about solving. And just to step back and look at the big picture again, why are we solving for these? Well, we want to find the torque that this guy has to apply. So if we know the normal forces in either direction, then we also know the total torque acting on this guy, which comes from the frictions, and then we know that we need to apply a torque to overcome that. So if we get these normal forces, then we've almost solved the problem. So we're going in the right direction. But let's keep moving. So now how do we solve these? Well, this is just a little algebra, so I'll just give you the gist of it. So let's call this equation 1 and this equation 2. So multiply, this is the standard, eliminating the variables we don't want. So multiply 1 by the quantity 1 minus mu, and 2, the lower equation, by 1 plus mu. So when we do that, we see that this guy will have an n sub r times 1 minus mu times 1 plus mu from both terms, and this guy will also have an n sub r times 1 minus mu, 1 plus mu, and they have opposite signs, so these two will cancel if we add them. Then add to find, when we do that, together we find, so the top one gets an n sub l times, this has two factors of 1 minus mu we multiplied by, and then the bottom one has n sub l times 1 plus mu, but we multiplied that again by 1 plus mu, so we got two of those, and then that equals, we multiplied again the bottom equation by 1 plus mu, so here's the 1 plus mu. So then when we expand these out, we'll get n sub l times 1 plus 1 is 2, the cross terms cancel, and then we have a 1 plus mu squared, 1 plus mu squared, so this will be 2 n sub l times 1 plus mu squared equals square root of 2 mg 1 plus mu. Or when we solve, let me give us a little more room. This means that the left normal force equals, we'll get a factor of square root of 2 downstairs when we divide, and then 1 plus mu over 1 plus mu squared. And I won't show you, but you can do the same sort of reasoning, plugging back in to get the right normal force. That's mg over square root of 2 times 1 minus mu over 1 plus mu squared. So now we're almost done. We found these two normal forces, which I remind you are related to the friction forces that we're interested in because they generate the torque that we're trying to oppose. So now all we need to do is notice that the total torque is given by the radius times F sub L plus the radius times F sub R, since they both torque in the same direction. So let me just write that down here. So we're almost done. The torque switching color one more time. So torque equals R cross F. There's two forces, so this will be the radius R times the left friction force plus the right friction force, which is the radius times mu times the left normal force plus the right normal force. And now we can add these together in our head almost. So when we add these, the two numerators interfere in that the mu's cancel, the plus mu and the minus mu go away. The 1 and 1 give us a 2, and that 2 cancels the square root of 2 downstairs to give us the square root of 2 upstairs. So we'll find the torque, the size of the torque, equals, we'll have an mgr square root of 2 and a mu upstairs. So square root of 2 mgr mu, and in the bottom 1 plus mu squared. So that's the torque generated by the two frictional forces, and that means it's also the torque that we need to apply, or the guy spinning the cylinder has to apply, in order to keep it rotating at the same angular velocity. So I think I agree with the star in the book that this problem was slightly more challenging, mostly because it gives you a problem without much of a diagram or breakdown. It's not at all obvious, looking at this diagram, that these two normal forces have different sizes. They're different because it looks very symmetrical, but the normal forces are different, and that's the key feature, because finding those two different normal forces then gives us the friction forces and thus the torque that we're interested in. So this problem was kind of hard because you had to kind of set it up and figure out that intermediate step without much guidance on your own. But besides that, the actual computation, although it's kind of long, was fairly straightforward. So thanks for watching.